Hey everybody, it's Mr. N, and we are going to do the next lesson, and this is how to find the area between curves. So, if you recall in the last chapter, what we did was we were finding areas under the curve, and so that means if I had a curve such as this one, right here, we said we would integrate. Okay, first we did the whole process of doing Riemann sums, and we did all these things, and then we came up with the fact that the integral is the Riemann sum, and we had FTC, and part 1 of FTC, or whichever one you want to call it, part 1 or part 2, said that the integral is the area under the curve. And so that's where we're at right now, is the integral is the area under the curve. So all the problems we did were bounded on an axis like this. You had your y and your x, and so we just took this and we integrated it. So whatever this curve was, f of x, or f of t in this case that's written, and the area ended up being f of x when we integrate on the bounds from a to b. Well, what if you've got two curves? What if you want the area between something sandwiched in between this top curve and the bottom curve? Well, the problem doesn't become any more difficult. All you're going to do is, if you want to find the distance from here to here, what would you do? You'd take the top piece minus the bottom piece. That's how you found the height over here. So like when you went through and you found this height, really what you did was you took this f of t and you subtracted it from 0, because that's where this was at 0. But now we've got an f of x up here and we've got a g of x down here. To find this height, I would just have to say f of x minus g of x, because everything was based on rectangular heights. So I could do the same process and make rectangles in here and do left or right or midpoint or trapezoid, but we're not going to do that. We're going to do integrals. So right here is where I'm showing you can do these rectangles, and the height of the rectangle is just going to be the top curve minus the bottom curve right there. So again, here is just restating that. It's the height that's the top curve minus the bottom curve. But we now do it with integrals, which is much more efficient. And so the area A of a region bounded by the curve is y equals f of x and y equals g of x. And the line x equals a to x equals b, where f and g are continuous functions, and assuming here f of x is greater than g of x, right, because you want a positive value, the area is just going to be the integral from a to b of f of x minus g of x. So the process is the same exact thing as what we've been doing. It has not changed at all, but now we're just having two curves, so we're going to take the top curve minus the bottom curve. And remember, since the integral is a distributable function or operation, we're going to integrate this minus the integral of that, or we can combine these two somehow and do it that way. So let's look at our first example, what we got here. We need to find the area of the regions bounded by the curves y equals x squared and y equals negative x plus 4x. So let me go through and quickly graph what each of these looks like. And y equals x squared is going to be this curve. We'll do that in a red color that goes like this. And y equals negative x squared plus 4x will be this curve that looks like that. Now, where are they going to intersect? That's our first step, is to find these points of intersection. Well, looking at this, I know that they're going to intersect here at 0, 0, and then they will intersect right up here somewhere. Okay, so that we're going to say x squared equals negative x squared plus 4x. And the reason I need to do that is I need to find this region from A to B so that I can find the area right in there. All right, so over here, I'll end up with 2x squared minus 4x equals 0. Take out a 2 and an x, and I'll be left with x minus 2. So they intersect at 0 and 2. We already indicated the 0. So 0, 0, and then 2 comma something. Let's plug it back in. We're going to get 4. And I plugged it back in here or here. It doesn't matter. So those are my points of intersection. So now I know that I'm going to integrate this from my A point, which is 0, to my B point, which is going to be at 2. So in the x, I'm going from 0 to 2. Remember, we take these slices going along the x for this particular problem. So we are going to end up with the integral from a to b of f of x minus g of x dx. That's going to be our area. Our area will be the integral from 0 to 2. The top curve was negative x squared plus 4x minus the bottom curve was x squared dx. Let's clean all this up, and we'll end up with the integral from 0 to 2 of negative 2x squared plus 4x dx, and then we can go ahead and finish this integration, and I'll get negative 2/3 x cubed plus 2x squared on the bounds from 0 to 2. Plugging this in, I'm going to get negative 2/3 times 8 plus 2 times 4 minus the 0. The area will end up being 8/3 square units when you clean all that up. All right, let's try the next one. Over here, find the area of the region bounded by these two curves. I'm going to slide this up even more because I'm going to utilize a bunch of space here. Now, one thing to note is we want to always first graph these so we know what we're looking at. And now, here's another thing. I took, in this first example, my slices like this, and I made these with delta x with a height of this, right? This is your height, there was your width. Your dx's were width, how we've always talked about it. So you don't have to do it that way. You could have done it integral along the y. So if you chose to do these horizontally, let's do a different color, in this manner, well, then you would have dy's as your thickness or the width of the rectangle, and then this would be your height. I'll explain that in the second problem because I'm going to show you two different methods for this one. So let's first start by graphing this. Here are my two curves. Now this is going to intersect at two spots, but let's first graph this. The first is x minus 5. I'm going to do this one first because it's a little bit easier to do that one. So over here, this is going to intersect negative 1, 2, 3, 4, 5. When I put in 0, and then when I put in 1, 2, 3, 4, 5. So that's going to be this line that looks like this. Okay? The next one is going to be a curve that intersects over here. It's going to be y squared, so it's going to open up horizontally. And then if I put in 1 for x, I will get 0 for y. So let's kind of quickly graph what something like that would look like. 1 for x, I get 0 for y. And then this ends up going in this manner and in this manner. Okay, let's find these points of intersection. Now this is not drawn to scale, so these points may not be perfect for what we need, but we'll see what we can do here. And let's set these equal to each other to solve. So what I'm going to do instead, though, is I'm going to go ahead and put this equation into the y right over there. So I'll end up with x minus 5 squared equals 2x minus 2. This becomes x squared minus 10x plus 25 equals 2x minus 2. Because if I did it the other way, then I would have to take the square root and it becomes a little bit more complicated. Or I would just have to solve for x. But in any case, here's what we have so far. So this is going to be x squared, and then over here I'm going to subtract the 2x minus 12x plus 27 equals 0. And this will factor into x minus 9, x minus 3 equals 0. So x is going to be 9 and 3. And so then this point over here will end up being at 9, 4. And this point will end up being at 3, negative 2. Okay, now that we found the points of intersection, we can start setting up our integral. But wait a minute, we have a problem here. Okay, let's see what our problem is. If I start with here and say the top curve minus the bottom curve, top curve minus the bottom curve, top curve minus the bottom curve, top curve, uh-oh, what do you notice happen right here? The curves change. This f of x, if I call that, and this g of x, at this point right here, right at that point right there, the f of x is the f of x. So we end up with two different regions. So I have to set up two different equations to find the area. In other words, I've got a border here, 1, 2, 3, this is at 3, doesn't look so good, but 3, -2, in which I need to set up region 1 and region 2 right here. So to find the two different areas. So the area will be the integral of region 1, well, I shouldn't say integral, I should just say region 1 plus region 2, which ends up being the integral from 1 to 3 plus the integral from 3 to 9. So from 1 to 3, right here, I've got a different equation different set of equations than I do from 3 to 9. Well, the 1 to 3 equation is this one. Now, this one, we need to be careful because when we look at this, we've got two parts to this. We've got y equals plus or minus the square root of 2x minus 2. So y equals positive root 2x minus 2 and negative root 2x. Negative, let's put that out. Negative root 2x minus 2. So there's two parts to that. Whereas this one, we're going to say this is the negative version right here is what I should highlight for you guys. And let's see if I can highlight that in another color. That is the negative version right there. Okay, so let's see how we can set this up. So let's go through and set up region 1. Region 1, and I'll do this as two separate problems. Region 1 is going to be the integral from 1 to 3 of this top curve, which is the positive part of the 2x minus 2, minus the bottom part, which is the negative root 2x minus 2 dx. Region 2 will be the integral from 3 to 9 of, now we've got the top part, this root 2x minus 2, minus the bottom curve, which is x minus 5. Be careful, put that x minus 5 in parentheses. Some of us, we will forget to distribute that negative, so we need to be very, very cautious of that. All right, so now let's finish the problem over here. Region 1 will be the integral from 1 to 3, and I'm going to combine this a little bit and clean this up. So this will be 2 times root 2x minus 2 dx. And when I integrate region 1, I'm going to get, I can use a substitution rule, or if I can think about it, that this is to the 1/2 power, it's going to end up being 2x minus 2 to the 3/2 power, like that. And then you'll need the 2 you already have, so we're going to have the 2 out in front. But then with the chain rule in here, I'll end up with another 2 out in front. So I will just need, which will reduce itself out. So all I need out in front of this is a 2/3. If that confused you, do a substitution rule. If me talking in my head confused you, because sometimes it confuses me, just do a substitution rule. So that's what it would end up being right there. So then this would be 16/3 minus, when you put in the 1, you'll get 0. So you end up with 16/3. Okay, region 2 will end up being the integral from 3 to 9 now of this equation right there. And I really can't clean that up much, so I'm just going to go ahead and integrate it as is. The only thing I'm going to just change is to be minus x plus 5, just like that. Okay, and so then region 2 will end up being, after you integrate it, that'll be 1/3, and this is going to be this 2x minus 2 to the 3/2. Again, that's how, this is why this one's 1/3 and the other one was 2/3, because I had that 2 out in front of it, minus 1/2 x squared plus 5x on the bounds from 3 to 9, and I will go ahead and save you the headache and tell you that this comes out to be 38/3. Okay, when you plug in the 9 and plug in the 3, it's going to come out to be 38/3. Okay, so trust me on that one. So adding the two regions together, I'm going to get 18 square units. Okay, now some of you may be looking, some of my brighter kids are looking at this going, what did you say above about going on horizontal? Well, if I take my slices this time and I go, okay, well, what if I took my slices this way? Okay, and I found the area going like that. Well, if you did that, that works. And you'd only need one region if you did it that way. But how would you do it that way? Well, this time, since you're moving in an up direction, you're going to start and you're going to take dy's. So let me do method 2 right here for you, which is with dy, because you don't have to find the top minus the bottom. You can find the right minus the left, right minus the left, but then you're moving in an up direction, right minus left, right, all the way up. So you need all these little slices like that, shaded region going vertically. So since you're going in a vertical direction, we're going to need a dy, because we're going to go from this y value to that y value. I'll call this one C and I'll call that one D. So we can say, and let me do this in a whole different color over here, and I'll do it in that green color. And we're going to say, you could say oops, wrong one there. We're going to say the integral from C to D of, now this will be our g of x minus our f of x dx. Now, what do I mean by C to D? Well, this is going to be my C value. This is going to be my D value. I'm going to go up in the y direction. So this will be the integral from -2 to 4. These are my two y values. Okay? And I'm going to say this is the right minus the left, just like that. So the right equation was y plus 5. Whoa, 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 whoa. What did I put it in y? Why did I did it right here? Right here, I'm going to say this becomes y plus 5. Whoa, stop. Why am I putting it in y? Because I screwed up here and I should say dy, because I need it in terms of y. So this will be g of y minus f of y. That's what I should have said to you guys there. It's g of y minus f of y. Okay, so I need it in terms of y because I'm moving in the y direction. Just like when I did the other problem and I was moving in the x direction this way, taking my slices that way. Okay, I was moving in the x that way. I need a dx. If I'm moving up in the y like this, I'm going to need dy's. Now later when we do volume, we're going to think about how we're slicing it. That's why I keep saying that word slicing. It's how I'm going to slice to find the area. So in this one, as I'm slicing it, it looks like this, right? And I'm slicing and taking these slices, and these slices, or these rectangles, have a dy width. So I need everything in terms of y. All right, so then I end up with this part of it, and now I can solve the other equation in terms of y, and that will be 1/2 y squared plus 1. So I'm going to add 2 to each side and divide by 2. So this will be minus 1/2 y squared plus 1. And that's solving this equation for x so that I have it in terms of y. And these will be dy's. Okay, so now what happened here is I only have one region to worry about, one region to work with. So again, solve these equations up here, and that's how I got these right there. All right, so now let's go ahead and clean this up, and I'll have the integral from -2 to 4, and this will be 1/2, -1/2 y squared plus y plus 4 dy. And when you integrate this, you're going to get, this will end up being -1/6 y cubed plus 1/2 y squared plus 4y on the bounds from -2 to 4, those two y value bounds, and this will end up being -32/3. I'm going to save you the headache and tell you what these are. Plus 8 plus 16 minus 4/3 plus 2 minus 8, and guess what? You get 18 square units. Same answer as above. This right here, in my opinion, is a much cleaner method than doing two regions. So you'll always have to examine and see, can I break this up into one region? Do I need two regions? Well, it always depends on the problem. All right, take a look at what we have next. Right here, it says find the area of the region bounded by these two curves. So I'm going to go ahead and sketch a graph of these curves for you. And these curves will look like this. And this will go, oops, let's go ahead and use a different color for the first curve. This will go up and down and back up. Okay, I'm going to extend this out a little bit. And then the next one will be down and kind of through here, and then cuts through right there. Okay, and this one is kind of like this, a little smoother. All right, so that's what these two curves will look like. So let's see what we can do with this. And that means I've got a couple regions here. No matter how I do this one now, I'm going to have region 1 and in here region 2. So whether you do this with vertical slices or horizontal slices, you're going to get two regions no matter what. And on this, you might as well just go vertical because these are two different equations as I go along, and these are two different, I'm take my slices to be dx's, because the top minus the bottom, top minus the bottom, top minus the bottom, top minus it's just at this point right here, they switch to which one is the top and which one is the bottom. So notice how the curves switch. Now, go through and find the points of intersection. In fact, you could find the points of intersection on your calculator. I'm okay with that for this particular problem. So the points of intersection, they intersect at, and I'm going to go ahead and save you the hassle, 0, 0, and 3, negative 3, and 4, comma 0. Okay, so this is 0, 0. This right here is 3, negative 3, and this point is 4, comma 0. Okay, so that means when I set this up, and I'm going to do it separately, I will go ahead and find each region. Region 1 will be the integral from 0 to here, which we said was at 3. So region 1 will be the integral from 0 to 3, and this is going to be the top curve, which is this x cubed curve, x cubed minus 6x squared plus 8x, minus the bottom curve, which was x squared minus 4x dx. Region 2 will be just the other way around. This is going to be now from 3 to 4, and now it's going to be the x squared minus 4x minus, this will be x cubed minus 6x squared plus 8x dx. Okay. So cleaning each of these up, I'll get the integral from 0 to 3, and this will be x cubed minus 7x squared plus 12x dx when I distribute the negative, combine like terms. So region 1 will end up being 1/4 x to the 4th minus 7/3 x cubed plus 6x squared on the bounds from 0 to 3. And I will again save you the headache, and that's going to be 45/4. Over here, region 2 will end up being the integral from 3 to 4 of negative x cubed plus 7x squared minus 12x dx. So region 2 ends up being negative 1/4 x to the 4th plus 7/3 x cubed minus 6x squared on the bounds from 3 to 4. So region 2 will be 7/12. Adding these two regions up, I'll get a total area of 71/6 square units. All right, now one more problem. We do have review problems on the midpoint rule we will do later, but just for these area ones right now, one more problem, and let's see what we end up with. So for this one, it says find the area of the region bounded by y equals x squared and y equals sine of x. So y equals x squared looks like this. Let's go ahead and do this. My lines have been horrible. I need to start using the tool here to make straight lines because mine have just been horrendous in this video. Maybe they're horrendous always, but I don't know. Okay, so x squared looks like this. Sine of x looks like that, okay? So this is my two intersection points. One of them is obviously easy. This is 0, 0, right? Let's go ahead and see if we can find the other intersection point. Let me put this in a different color, 0, 0. Well, how are you going to find the other intersection point? Well, you're going to want to say, well, when x squared equals the sine of x. Well, we're going to say x squared minus sine x equals 0. This is too hard to solve. So we need our calculators. And we can graph each in our calculators, have our calculator find the point of intersection, and that point of intersection is going to be 0.87673.76865. Okay, so that's where this point of intersection is. So we need the area from the top curve minus the bottom curve, and we're going in the x's like this across. So we're going from 0 to 0.87673. The top curve is sine x minus the bottom curve is x squared dx. Just like that. Well, now doing this is, well, you could do it by hand. You're going to get negative cosine x plus, or we should say minus 1/3 x cubed on the bounds from 0 to 0.87673, and then just use a calculator and plug those in. Now, if you wanted to, and you will end up here, I'll tell you what the answer is real quick, 0.1357 square units. Now, if you wanted to do the whole thing on your calculator, you would use the features that we've been using. Hit the math button, hit FNINT, just like I've taught you how to integrate with your calculators. If you have the new software, it'll open up the integral. And then just put the whole integral in with respect to x, hit equals, you'll get that. If you have the older software, you're going to have to do the parentheses thing, and you'll have sine x minus your x squared, and then you'd have to do comma from x from 0 to 0.87673, like that, at that. Now, depending on the software you have, most of you will have the new software, and you just put in the integral, hit enter, and you get your answer. So that's how we can do it on our calculators, and this is definitely one where you're going to need to do it with your calculator. All right, so thanks for watching. Have fun with these area ones. I will see you guys in the next video, but make sure to hit that like and subscribe button. All right, guys, see you later.